Apple II forever, making life better and better. Apple II forever and ever, bringing the rainbow to you.
Hello everyone, welcome to this virtual KansasFest session. My name is Olivier Zardini, and I'm going to present you today our next to be released software named Siren. This is a cross-platform development tool used to improve the debugging of Apple II and Apple IIgs software running on an emulator. This 30-minute session will be divided in 4 parts. As first, we are going to discuss about the way we were developing software in the 90s and the way we do it now, and what are the still missing features which at the end drive us to create Siren. So we'll discuss about Siren architecture, his interaction with operating system, Windows here, and his integration with a popular Apple IIgs emulator named KEGS. So we'll demonstrate the software in 2 ways. First, by using the software to analyze live running application on the Apple IIgs emulator, and at the end, showing how Siren can be used in the development of Apple IIgs programs. Our history with Apple IIgs programming starts at the beginning of the 90s by the release in 1992 of a game named Art. So we quickly moved to the adaptation of existing software on other platforms, such as Tiny, which is coming from DataRST, Cogito, that we adapt from the Macintosh, Blockade, that was coming from my Spark workstation, and Lemmings, which was a mix of Apple DataRST, Amiga, and Macintosh settings. Sometimes we were also needed to adapt or develop our own in-house software, like utilities. For example, the color screen of Tiny's is a 3200 color screen, and at the time in 1993, there were no available graphic converter for such pictures. So we have started what will at the end be released as Convert 3200, a software capable to adapt high color Macintosh pictures to the Apple IIgs screen. The way we were developing software at the time was about always the same. First, we have to locate the hardware running the software. So it could be an DataRST, Amiga, and so on. And so we have first to run the software on the source platform, find a way to extract the content of the game asset, like graphic and so on, and transfer this to our Apple IIgs, where most of the job was done. Depending on the platform, getting the game asset was sometimes easy, for example, for the Macintosh, where most of the assets are located in resource file, but for other platforms like DataRST, it was much more complex. And the DataRST doesn't have a way to easily grab the resource, so we had to buy an extra little hardware card that can be used to stop the game and pump memory data. Okay, once we have all the data from the source computer, we had to put this on a floppy disk at the time, and we were needed to bring such a floppy disk on the GS. When the source was a Macintosh, we were using Apple IIgs on the Mac to write everything on the 800K disk of Macintosh that can be read directly on the GS. When it was PC 724K disk, we were simply using the blue disk card I had on my Apple IIgs, which was capable with a PC drive to read such content. At the time, all the development and work on the game asset was done on our Apple IIgs. Antoine and I as what we can call high capability Apple IIgs. So basically Apple IIgs containing at least 4 megabytes of memory extension, an accelerated Apple IIgs. Mine was running at 9, I think Antoine was 8. Of course, we had a high-speed SCSI card and an hard drive. Of course, at the time, the perfect companion was an image writer to printer because it's not with 20 lines of code that you can read a lot of. So printing the source code was, of course, something we were doing on a regular basis to analyze what we were writing. I already speak a little bit about the blue disk card, which was here ready to simplify the exchange between the DataRST or PC with the IIgs. And of course, on the Apple IIgs, we were running GSWEX 601 at the time. We were using Merlin 16 to write code, using Dream Graphics and Iconade for all work about graphic asset, and of course, using SuperConvert to convert pictures coming from the DataRST or the other platform to have some Apple IIgs ready for use graphic format. The Lemmings development took us about 8 months to be completed from the very beginning up to the release of the software. These 8 months will be about divided in two parts. The first 4 months were used to grab all the game assets, pictures by picture, sprite by sprite, and it took about 4 months between the Atari ST and the two GS. The real development part on the GS side took about the same time, 4 months. The conclusion of the Lemmings development was that, okay, it was possible to do the thing like that, but it was too much time consuming. And creating every software with 4 months to extract all the resources was probably not the right way to do. And that will be a lesson we will learn for next days. We stopped our Apple IIgs development in the late of the 90s, and we went back 10 years later, but with this time with a new idea. Instead of using the same old ways method, this time we were ready to improve the Apple IIgs development, especially by creating a set of tools we can use on modern PCs to not only speed up the Apple IIgs development cycle, but also to increase the quality of the software. What we learned from Lemmings' experience was that we really need to improve the way we were getting game assets. Spending 4 months for just grabbing all the assets from one game was clearly too much. So we have started by creating a software named Window Capture, capable to record the output of any game running on emulator on a modern PC. So the same year we provide KEGS, which is a disk utility capable to write file available on a PC directly on the Apple IIgs disk image format. The year later, we provide Mr. Sprite, which is a way we can compile sprites and technology. So we basically compile sprite asset to end up with code, and this code will push the sprite on the screen in a very efficient way, because of course Apple IIgs doesn't have any sprite handling hardware routine. The same year, we also work on a generic file compressing format named LZ4. Of course, it was publicly available for any platform, but the Apple IIgs unpacking code was missing. 2 years later, we have provided Merlin 32, which is a modern version of Merlin 16 we were using back in the day on the Apple IIgs. This is a very key asset here because it lets you on a modern PC, Mac, Linux, to write your code and automatically create the output file by assembling it in 1 second. 3 years later, Studio was ready. Studio has not yet been released. It's reverse engineering tool that take as a startup the output of many of the well-known emulator for classic machine like the Atari ST, the Amiga, the PC-DOS, and so on. So starting from the output of this emulator, Studio can grab resource of any game, the source code, and the game assets, the sprite, and so on. And in 2022, we have decided to say, okay, it's probably time to test all of this chain of new modern tool to see how far and what we can do with that. So it started as a joke, and we say, okay, can we do one software a month on this year? It was also the 30 years anniversary of Brutal Deluxe Foundation. And with Antoine, we say, okay, let's do that. So during this year, we have pushed one new software a month. So we have the Dragon Slayer series, Space Ace, Passenger of the Wing, and so on. And at the end of the year 2022, we did. And so the 12th software was available. The new way of creating software for the Apple IIgs starts usually with, of course, the emulator running the software on the source platform. Could be an Atari ST emulator, Amiga emulator, DOS emulator, anything. So basically, we first ask to set up the emulator, find the disk image, and run it. Okay. From the source emulator platform, we usually have a settings to dump the memory content as a memory snapshot. And also, we record the screen using window capture. So with the capability of Studio to analyze the memory snapshot of the platform, plus the window capture capable to record the sprite animation settings and so on. At the end, we can easily grab game assets. So basically, we grab the sprite and the sprite movement details thanks to window capture. We grab background screen, color palette, sound, code, game data, and so on. So now the capture process of the data of the game is pretty efficient and pretty fast. No more 4 months anyway. So as soon as we are ready with everything that we need to create the game, the development itself starts and works on modern PC. So basically, Merlin 32 is used to create the code. KEGS is used to automatically add the output of Merlin 32 on a disk image. Mr. Sprite is here to compile the sprite as a binary way. LZ4 is used to compress everything and uncompress on memory. And Studio is also here by helping in the sprite animation process, the creation of the icon, and so on. As soon as Merlin 32 has assembled all the code, we run automatically one emulator. Here, this is KEGS. And with first way, we can quickly, easily test the game visual. We can test the sound, we can test the music, we can test the game logic, we can also test the control. And most of the time, this is a cycle between the development part and the test part, okay? When everything is okay on the emulator, at the end, of course, we need to test on the real PC, which is our Apple IIgs. But this time, unlike we did in the 90s, the Apple IIgs is only used at the end of the process just for test. And so we don't need a very big Apple IIgs machine, no more hard drive and so on, no more accelerated Apple IIgs. A basic Apple IIgs is enough because it's not part of the development process. It's only here to test the final results. No surprise that it's not because the software is running on KEGS that it will run on the real Apple IIgs. You have many things you need to test on real hardware. For example, what happens if you unplug the joystick when you are playing? What about hardware like the 4-play cards and so on? So we still need the Apple IIgs, but we can say that Apple IIgs is only used something like about 8% in the total process of creating new games. Even if the usage of such cross-development tools have simplified the Apple IIgs game creation, we still have some issue during the test step of the creation, especially on the emulator. Our top 3 missing features are, of course, the step-by-step run for 65x16 code. Okay, we would like to run instruction by instruction. It's not possible because there is nothing at the processor level that can stop an execution after running one operation. What we would like also to have from the emulator is capability to run in slow motion. For example, we are drawing a sprite on the screen. We would like to slow down the emulator so we can see pixel by pixel put on the screen, for example. What is also important, the capability to record operations. For example, if you are debugging an unpacking routine, it could be thousands of lines of code, and on a specific line of code, something is going to happen. And you don't want to make new next operation. We would like to have a record of the 1,000 line of code somewhere on the file, and so you can find and learn from it. What also could be very useful on the emulator is what we call a multiple data view. Most of the time, what you see on the emulator is what the GS want to show you. Basically, if it's a game, you will see the output with the current graphic page. Of course, what we would like to see is what is behind. For example, if you are double switching from bank O1 or bank E1, you would like to see what is not displayed currently on the screen. You will also want to follow what is happening in other part of the memory. What could be also interesting is to get input or output from the emulator. So we have to patch a little bit KEGS to be able to extract the data from the emulator to be able to analyze what was on the memory at the time. Sometimes we can use the debugger, but they are pretty hard to use, especially you have to read documentation and everyone has a specific and different way to debug. What we can find also hard to find and analyze is the interrupt. On the interrupt on the Apple IIgs, you set up an interrupt, but you never know exactly when you are going to be called. And so it's hard to see how interrupts interleave in your running code. What everyone is dreaming is a memory usage control. Using assembly language, you can write in any part of the memory. If you do something wrong, you can corrupt a part of memory which is not yours, and this is nearly impossible to trace. What is also interesting is to follow the Apple IIgs internal access. It means what happens when you access a file through FST and so on. Most of the time, you call the GSOS layer and you never see what is behind. So of course, it could be very interesting to understand what is behind. And at the end, if you want to improve the game of the program we are running, could be interesting to have cycle counting on every operation. So if you write a function, you would like to know how many cycles does it take in your global pictures. Get all function statistics, how many times this function has been called, how many cycle minimum, maximum, average this function is taken. And of course, the profiling function, it means which function call which and so on. And if you improve a little bit your code, how you can at the end understand what is the percentage of usage in the total CPU of your current function. Due to all these missing features, we have decided to create a new software named Siren to help us to address all of these limitations. Siren software comes in two parts. The first part is a Windows 64 application running on any Windows. Currently, it's only one exe file, no DLL, no dependency, nothing. It's about 1 megabyte size, 85,000 lines of code, writing mostly in C language and using only the Windows 32 layer. Should work on any version of Windows, modern or old one. And a second part, which is a Siren interface layer, which is a plugin for emulator, which is also C language Windows 32 based code. And this is a source code. So basically we have to modify a little bit the emulator. Here we choose KEGS as an example, but it could be any Apple II or Apple IIgs emulator. And so this code interface with the emulator has 3 levels, an init level, an exit level, and in next op level. It means that every time the emulator wants to run an operation from the microprocessor, it has to call first the Siren interface layer to know if it can do it or not. As soon as Siren is connecting through the interface layer to the emulator now stops. So we can see Siren as a remote control for the emulator. The inter-processus communication between Siren and the emulator goes in 2 ways. First, by using the copy data Windows message, and also using a 1 megabyte shared memory space. So shared memory space is efficient because both executables can write together and exchange data very efficiently. And copy data Windows message are efficient because they are processed as a list. So if KEGS is sending a lot of message to Siren, Siren will process this message in the same order that they have been sent by KEGS. Siren is receiving information and data from KEGS basically in 2 ways. Operation data, so for every operation by the microprocessor, there is a 59-byte set of data which is sent to Siren to be processed and analyzed. And also on demand, KEGS can also send all the content of his memory space, the RAM, the ROM, the doc RAM, doc register, and so on, up to Siren for extra analysis also. Siren interface layer take care of the breakpoint engine, which is running directly in the same space than the KEGS in order to enhance the processing of the breakpoints. The breakpoint definition are sent by Siren on the 1 megabyte shared memory. So now let's see Siren in action, and in the first time that will be to analyze current running application on KEGS emulator. Okay, so here we find a standard KEGS installation on a Windows machine with his home file and the settings, and we also put Siren in the same folder. So starting KEGS won't be different as we do it usually. The only little difference could be seen on the output window where you can see Siren integration and the fact that the Siren layer in KEGS say, okay, initialization was okay. So we can start Siren just to have both together on the screen. And if we want to connect Siren to KEGS, we simply have to ask attachment to the emulator, and we select KEGS window. And at this moment, now Siren takes control of KEGS. The next to be run operation is that one. So currently the next operation would be CMP. And so we can ask KEGS to run one by one operation now. In the upper window, we keep trace of all operation history. We can record if we need. So basically, we can record all operation, and the lower part is the current disassembly of the code. Here we see the call stack of operation. So basically, this line of code has a GRSR to this address, and a little bit later, you have another GSR and so on. So here we can see the call. We can run operation one by one. We can operation 10 by 10 if we want, 100 by 100, and so on. We can also ask to go to the next jump operation, or any jump, BN and so on. We can ask to go to the next function, the next end of function. We can ask VBL by VBL, so running part of, and so on. We can ask for the next interruption, the next toolbox call, or the next GSOS call. Okay, so this is a way to ask KEGS to go on a specific next address. Of course, I can ask KEGS also to run as usually. And here we can see that we are getting more and more operation. I can stop also. And what you can see here is a number of operation which has been queued between the Siren, KEGS and Siren. So currently Siren has recorded 29 million of operation, counting for 120 million of cycle. This list of operation can also be seen here, but of course can be put on a file to be analyzed. We can ask to be detached from KEGS at any time if you want to let KEGS to run on its own. Okay, so let's start one Apple IIgs software running on KEGS just to see how Siren can be helpful to understand what's going on KGS side. Okay, so as you will recognize, this is Filmazed from Jason Harper, which is a nice demo on Apple IIgs running. And so once again, we can ask Siren to connect to the emulator. As soon as we have attached, the software frees, of course, on KEGS part. We can remove this for the moment and focus a little bit on the code here. So we have numerous way to see what's going on the Apple IIgs side. We can start by graphic HGR, which is a window we can use to see exactly what is going on the software. We ask 888 because the lower part of the screen is using high definition, where the upper size using the standard resolution. We can, if we want to have the same look and feel, ask for fill mode enable. And as you can see, we can see what is already drawn by the software and how, of course, the GS render the situation. We can also ask to see the palette and the SCB from the usage of the software that help us to understand how the gradient has been done here. We can continue and run the software, for example, VBL by VBL. And so slowly you can see the screen drawing one by one. Okay. Another interesting feature is the video spot. So this is currently location of the spot, and by adding 1,000 cycle by 1,000 operation by 1,000, we can see exactly where we are and when we draw the file. What's interesting is, as you can see, and we will slow down here. So we can go 1,000 by 1,000, and we are going to stop when we'll be here at the junction of the text part and the graphic part. So in this kind, we go 100 by 100 if we go to be a little bit slower, but here that's okay. So 100 by 100, and as you can see, as soon as the video spot enter this lower part, that will be the time for the software to undraw everything. So of course we can remove the fill mode, and so undraw part took few lines here, and if we continue now is rewriting the part of the screen. Of course we can ask for fill mode to be enabled to see what happened. And so here very slowly you can see what happened, and you have a control, so you know that every erase plus draw is done in the lower part of the screen. And that's pretty magic to see exactly how does that work. Of course, I can continue to run the software in real time if I want. Okay, so the graphic part is used to understand exactly what happened on the graphic page. Of course, you can not only look at the real page, but you can also ask for a view of any page. Basically here, this is the current data located on E1, but of course, as we have seen, most of the draw probably are done directly on E1 and not O1. Okay, we have many ways to see what happened also. So if we were looking at text page, we could also ask for the text page to be displayed, but in this case, there is nothing because we are not using a text part software. We can ask view on specific part of the memory. So at any location of the memory, you can ask for something. If you want to have a clear idea of what is displayed in the current page, you can ask, and you can, of course, adapt the number of picture byte per line and so on during your screen. You can also decide to access code, so you can disassemble any part of the software automatically. You can create as many disassembly line as you want. So if you need one window plus another one, no problem. Here I have a GSL to this. I would like to understand where it goes. So it's BBD0, BBD0. And here I am. So I can follow, I can create as many disassembly line as I want. I can also access to what we name Apple IIgs internals. So this is everything that the GS has internally, like all of his vector, the jump vector, the current value and the previous one. So if you want to know if someone has set a ERQ by just changing the location of the jump, it will be easy to see here, for example. Quick draw vector are also displayed. You can follow if application has modified something. This is the list of all applications currently loaded in the Apple IIgs memory. The path on the file, the current location in memory. You have breakdown by CDA, NDA, and so on. If you want to understand what this NDA is doing, you simply double click and it will give you the handle of the application. Here, that's to shadow right, and you can of course directly see the memory data. You can save or you can disassemble also if you want the code directly. You have the list of all init, all driver, all FST, and every memory, every handle of memory is displayed. You have the purge, the free handle, and so on. So if you want to follow one handle, that's pretty straight. You simply double click. You have the handle information here and a pointer to the data. So data can be disassembled automatically, and we can see code here, and automatically it recognizes, of course, Apple IIgs call. What is interesting also is we have another layer named memory map. Memory map is Apple IIgs memory from bank 1 to as many as you have. So I say it's 4 megabytes here. And every part of memory receive a color based on the kind of operation that took place. So basically, write means writes, red means write, for example. And so we say E1 2000 is, of course, a graphic page. So we see a lot of write on the graphic page. We can reset, of course, at any time. So if we run it again a little bit, the software is running, and in real time, you see the red part, the read-write part, the executable part to run. So what we know is currently the software is running in this part. And you can see if I put my mouse, it told me that this part is by FilmMaze, which is our current software. If I go and I select FilmMaze, automatically all the FilmMaze location goes in dark. And so I can see exactly where I am. This is executable plus write, so there is auto modification code. Most of the code is here. We can see write directly to the graphic page. So we have a lot of what we name views that let you see. Of course, if you are more in the sound part, you have access to the dock RAM. If you care about the dock register, you have the value in real time of a dock register and so on. So part of the analyzing is controlling the application line by line, group of line by group of line, or by VBL, for example. And you can record all operation, and you can view in real time exactly what happened inside the Apple IIgs memory. At any time, you can also save a memory snapshot of the current 4 MB of the Apple IIgs emulator to a file. So later you can reload this file into Siren, or you can use this file to be analyzed by other tool. Studio is also one of the tools we use to interpret the snapshot data of the Apple IIgs memory. So after this short presentation analyzing live application, now let's see how Siren can help in application development. Okay, so let's start to use Siren now with the software we have written named Apple IIgs Karate. The main difference between this demonstration and the previous one is, of course, that for this program we have the source code. So let's start the software. Let's go computer by computer and let's find what we can do. Okay, I would like to put breakpoint on the software, and I would like to stop the software. So let's connect first. By default, it stops where we are. Okay. Now we have the source code and we have the symbol file. So we ask Siren to load the symbol file of Apple IIgs Karate created by Merlin32. And as soon as I do that, I can see now I have labels everywhere. And of course, the source code is easier to read. What I would like to put is two breakpoints. One for the getRandom function. I would like to be stopped every time this function is called by the software. But also, I would like to know the value returned by this function. And we saw that output number is sent to A accumulator. So around GRN exit label, I would like to print the return value of the accumulator. For that, I simply need to enter in the breakpoint part, create a new breakpoint based on symbol. Let's select the getRandom number name and add a getRandom number here. I want to stop on execution on this label. Okay, that's perfect. And I'm going to enable the breakpoint. I'm going to create a second breakpoint, this time on the GRN exit label. So once again, let's pick it from here, GRN exit, that's the one. And this time on execution, I don't want to be stopped, but I would like to print something. So let's put GOID, which is a global operation ID, and I need to put a random number output, and I put the random number into A accumulator. I put this in bracket just to display it in the output location. I'm going to enable this breakpoint, and we are ready. Let's run KEGS. Let's run the game. And as soon as we reach the getRandom function, everything stopped. As we can see, the function playGame called function playLevel, which itself calls sprite engine, which itself and so on. And at the end, we have getRandom number called. Okay, I can continue to run, but every time the function is called, we have a stop by the software. In between, we can see here the print of the random value of every call of this function. I can, of course, at any time disable the breakpoint. For example, I'm going to disable the stop one, but I'm going to keep the one who print. I'm going to run, stop when needed, and I can see in between all the value, and as I can hope, the value are nearly all random. I can continue. Let's stop the execution of the software. So we go back at the beginning and we stop here. So basically we had a full loop of game execution. And now I can have some statistics about my functions. So here we have the list of all the functions. Of course, I'm going most interesting by the one inside Apple IIgs Karate. So how many times they have been called and so on. So let's sort by name, and I'm going to grab of my function altogether. So I can find all my random number of function has been called 20 times. The total number of cycle spent by this 20 call was 1,480 cycle. The minimum number of cycle took by the function was 74 cycle. Min and max are about the same. It's not the case for all function, of course. So that's interesting. You know how long, how many times every function has been called, how long it took, and so on. Another interesting part is what we name the profiling. So basically, we were in the root process here, and we have called the play game function. So, and for the moment, the total percentage size time was 0 simply because we didn't have play a lot. But if we enter, we have the number of time we run. Play level was the one who took the more time, and so on. So play level itself called get index, load, unpack, and so on. So you can follow all the sprite engine has been called 3 times and has 27 lower function and so on. So you can clearly go and find which are at every time the function taking the much number of cycle and the percentage. Of course, you can save this as a tree for a better analysis. Okay, even if the software looks completed and runs fine, there are few things that left to do before releasing and sending it to everyone. So basically, few things are missing. For example, the capability for Siren to send data, especially if we modify the memory and so on, back to KEGS. We would like also to track the doc RAM read and write, especially in the memory map where we have the colors. We don't track them now. We would like also to export the profiler information as a tree or graph. Could be interesting visually, of course. I have some work to do on the UI itself. For example, let's window to be resizable and so on. I need to improve a little bit the disassembly part. We'd like to bring much more built-in Apple II symbol so we can navigate in the source of the ROM more easily. Could be interesting to have a dedicated version of the memory map for the Apple II with a 128K with the language card bank and so on. Currently, we see the memory as Apple IIgs seat. Could be interesting to improve a little bit the KEGS integration. For the moment, I have not yet discussed with Kent about the way we did it. So probably we could make some progress in this part. And of course, we need to write the documentation, create a web page on our website for the product, and to publish, as usually, the software and the source code. Thank you for listening, and we are going to see you very soon in the Q&A.
Let me ask the some quick questions. Here's a hard one. I think KEGS does run on the Mac, but someone's asking, what about the Cyrene? Are there any plans? You have a lot of UI stuff.
Exactly. So you already know the answer. Basically, you have two ways. Or you try to put something that run everywhere. And at the end, like most emulator, you put everything on the small window. And basically, you use this window UI and you try to adapt everywhere. Or you take advantage of the current PC you have and you try to put window everywhere. Basically, we choose the second option, where we say, okay, we need visualization. I need visualization for my code, for my text, and so on. So I can't put everything on a single window. Antoine is using the software on his Mac using Parallel, I guess. The only Windows level is the Windows 32, so probably on Linux emulation should work, not pretty sure. Code is, of course, available as for all the other products that we provide. So if someone is motivated to redo something elsewhere, why not? Currently, yes, it's more, I would say, Windows-based solution. And it's more easy to emulate Windows on Linux and Macintosh than to do the opposite. So yeah, for the moment, and because software is a kind of work in progress, I would say that Windows only, but there is millions of PC all over the world, so I guess that you can probably find one to play with the software. Especially because also it doesn't need anything to be installed. So it's just one executable, you start from a USB key and it can work from any desk, I would say.
Jeff asks, he says, I may have missed it, but is there a feature for a slow run, basically an automatic single step with a delay between each step?
Not really. What we say slow step was more the idea to click the button as you have seen for 100, 1000, and so on. So the idea, once again, is as a programmer, you know what you do. And most of the time, you know if you slow down is more VBL by VBL or second by second, 1000 by 1000, and so on. So yeah, I would say that the speed is more the speed of your click and the button in the UI where you click.
Okay, fair. And let's see, Michael asks, are there bookmarks? And I'm assuming he's talking about bookmarks in the assembly code. And he says in Apple Win, for example, you can set a bookmark like to a number, and then you can hit another key to, I think, run to that bookmark. I believe that's
Yeah,
what
what was not in the presentation is on the little panel where you have the design assembly code, you can click anywhere, select the line and click on go to highlight. So so it's true on the little part of the disassembly. After you can use, as you have seen, the breakpoint to stop where you want. And breakpoint are based on symbol name. So when you reassemble your Merlin 32 code, automatically this creates a new symbol, which is automatically taken into account by the software. So when you save your breakpoint, because you have not seen it, but you can save your breakpoint, the save of the destination of the breakpoint does not take the address, but the name of the symbol. So when you restart, you don't care where is your exactly memory location. You can work only by name, and so you keep by name.
Okay,
But of course, if you want a specific address hard-coded, you can make the breakpoint by address.
great. Okay. Let's see, Jeremy asks, can you use similar information from a project which uses the Orca development tools, or is it just Merlin 32?
Currently, this is a new feature on Merlin, which has not yet been pushed to public. The symbol file is pretty straight and easy. So even if your software do not provide such one, you can probably easily make a converter that at the end will create the kind of symbol list file that we provide. Basically, on the Apple IIgs, you need a symbol is the name of the executable, which can be several segments. So you need the name of the segment and the location of your symbol in this segment. And this can be relocated by, of course, the GSOS layer. So we keep it that way. And after, you know if the symbol is code, data, how long it takes in byte, and so on. So in the disassembly part, when you are touching, I would say string, GSOS string, you will see the string. When you are touching code, you will see the code and so on.
Okay.
But we will provide detail about the file format for the symbol.
Okay. If somebody wanted to say add support, so that would happen automatically. I mean, are you guys open to people contributing to the project?
Currently, the project is in-house.
Yep.
It will probably on air, I would say September this year. Let's keep one more month to fix stuff and clean some stuff. There is also the part where we connect to the emulator, because once again, this is a demonstration with KEGS, but you can connect Siren with any emulator running on Windows, of course. So we also need to document the connection between the emulator and the Siren interface layer, if you want to take advantage of Siren with your own emulator. Of course, we will distribute Siren and KEGS together if people want to try it, but there is also a discussion for that part.
Okay. What about if somebody wanted to interface it with something like Apple Win, so more of a not a 2GS, but a 2E type emulator?
Yeah, that will be the same. So basically, as I said in presentation, there is 3 points, one init point, one exit point, and one next op point. So basically, probably you need one day to interface your code with Siren interface layer.
Wow, that is amazing.
One of the idea was really to do not put all of our energy and thought in the emulator itself. Everyone has already made a lot of emulator, so we prefer to make the emulator out to the debugger outside of the emulator, so we can continue to work. You can continue to work on your emulator, and we can join together. And if one day the emulator is fade out because the guy is no more here and so on, all the thing we did for the debugger part is not lost. It's still here, and we can continue to be linked to the next emulator.
Okay, that's great. I think that answered Scott's question here. He was asking about, will it work with 2E or 2C emulation? So it's
Yeah. The only thing that is missing probably is the memory map with the colors is very Apple IIgs oriented. An Apple II memory map will be more the first 128K with a language card bank and some stuff. So we probably need to create a dedicated view for this, especially when we need to analyze Apple IIe code, which is only stands in the 200 and the two first bank. It's probably hard to read.
I think we're kind of out of time. Antoine, did you want to say any last words? You were very quiet.
It's the work of Olivier. This is why I'm speaking today.
No.
I
It's
don't have
together
anything
work,
yet
of course.
to add. I'm just a tester here, and it brings a lot of usefulness. I used to disassemble a couple of software over time, and that kind of software, Siren, is very useful for that because you can verify that what you are doing, the assembly, is correct and behaves like the original program. So it's pretty good.
Great. All right. Well, thank you both so much. That was an amazing talk. And yeah, we'll look forward to seeing more of it online. So thank you.
Yeah.
Thank you.
Cheers.
Have a
Bye-bye.
great day. Bye-bye.